In this section, we're going to get started with the anomaly detection machine learning pipeline. As always, I like to start at the beginning talking about data collection. Because I'm going to say this yet again, you get the data collection part wrong, everything else down the pipe is a wasted effort. So let's try and understand a little bit about what it means to collect data for anomaly detection. Let's roll back a bit and reflect on some of the dataset principles that we learned previously. Here's an example of the speech command dataset, which we used in keyword spotting. Previously, when you wanted to do keyword spotting, you knew what the requirements were for the data set explicitly, because you knew what keywords were going to be, and then you could go about collecting the data for those keywords. So you got to be careful, of course, about gathering the right keywords under the right situations and making sure that the data is correct and making sure that you can sustain that pipeline. But there's one very important fundamental assumption, or the baseline, that you can take for granted here is that you know your keywords. And that makes a world of a difference, because when it comes to anomaly detection, you don't know your keyword. What do I mean by that? Specifically, you don't know the numerous ways in which a machine can fail. So when you're talking about anomalies, well, you need to know the 1 in 100 ways or the 1 in 1,000 ways a particular machine can fail. Compare and contrast that with keyword spotting or visual wake words data sets that we talked about. We knew exactly what we were looking for. And in the visual wake words, we knew the particular item of interest in those images. Was it a person? Was it a cat? And so here, you don't know which way the machine is going to fail. All you know is that you're trying to predict a failure, and that presents a real problem. So that's number one. Number two is that it's quite hard to capture, a wealth or a volume of data for something that is inherently very rare. Recall that you're trying to collect anomalous data. And what that means is that you're trying to collect a lot of data for something that happens extremely rarely. So it's really like, a very hard problem that we're trying to solve. And if you wanted to collect the data set very fast, either you'd have to wait a long time till the part wears out and fails, or you have to go about and buy machines and intentionally start breaking them. Well, that doesn't sound like an easy or a cheap thing to do. Usually you're trying to use TinyML and anomaly detection on costly machines because you want them, to predictively do maintenance on them and on these costly machines so that they don't break down at critical times. Well, you're not intentionally going to go down and break, 1,000 or 100,000 wind turbines just because, you want to be able to do predictive maintenance on, 1 or 2 of these turbines, in a timely manner. So think about that. So this presents a really hard problem for us because a normal data is usually a closed set, meaning that we know what the normal data operation looks like, and therefore we can easily capture the data because we have a lot of normal data. Abnormal data presents a really big problem because abnormal data is an open set. It's a set where the system can fail in any number of ways of different and unpredictable ways. And so it's the unknown unknowns. Therefore, we need some way to train a model to detect something we can't actually capture in our data set. So you need to be very clever about how you can actually engineer the system in order to detect these abnormalities. One of the biggest problems is that you have, unbalanced data in anomaly detection. In the context of traditional detector of cat versus dog and all the data engineering that we taught you, there was a lot of that data. And, just as much of cats versus as much as dog data, for example. And you could create, a balanced data set. And here, because anomalies are really rare, the problem you're going to have is that you're going to have very little data about the anomalies and a lot of data about, the normal operation. And that presents, a very unbalanced data set. So there's been a lot of interest in the community to try and build data sets for anomaly detection, specifically around sound. I'm actually going to introduce sound here because we've done stuff around sound and audio. So here's the MIMI data set that you should know about. And it's a data set that's specifically designed for malfunctioning industrial machine investigation. It's a collection of sounds. And what the data sets creators have gone out and done is they've instrumented things like pumps, fans, valves, and so forth, and capture different kinds of sounds that they make, both during normal operation as well as abnormal operation in real factory settings. So the spectrograms here visualize different kinds of sounds in different modes of operation. In fact, you're going to have a deep reading coming up on this, which is specifically on the MIMI dataset. So I'm not going to go too much deeper into this. The reading will do so. Now, this is the context of a real factory setting. What about getting creative in order to get lots of data, which is hard to get data? Well, there's the toy Atmos dataset, which is a really interesting way to think about collecting data. The toy Atmos dataset is basically a dataset of miniature machine operating sounds. The dataset happens to have over 540 hours of sound for anomaly detection. It's based on toys like cars, conveyor belts, and trains, and it's all about the sounds that they make, and you're trying to collect to detect anomalies from them. So you can see here on the setup, there's a track with toy trains. Yeah, there are toys actually, and they're actually going to be going around doing their job of continuously doing what a toy does. And there are different microphones that are positioned in different places, and their sounds are recorded. And one of the key things that the authors have done is that they have deliberately damaged the toys in different ways. So then you can collect different kinds of sounds to get a diverse portfolio of normal and abnormal or breakdown sounds in the data set. Now, looking one level deeper, the data set is spread across 3 different types of toys: a toy car, a toy conveyor, which is actually fixed, versus a toy train, which is actually continuously moving around the tracks. And so you get very different kinds of sounds coming from them. And you are collecting, different machine types of sounds over here. And so you're going to get a lot of data that's, actually, it's quite quiet, which is the background sound or the environmental noise. And then you have that operating situation, as well as the data, when the machine is actually running. Now, with that, you can actually think about how, to collect the data intelligently, because as I said earlier, there are 4 different microphones that they use. Why? Well, because you want to analyze the data from different observation points for diversity, so that you can use one microphone alone and it does not give you the full representation of what that sound would look like. And so there are a lot of nuances about how you actually collect the sounds. And so when you're building a model, for instance, you can decide, am I going to use the data that's coming from all 4, or am I actually going to use all 3 or 2 or so forth? The point is that there's a lot of diversity and flexibility in this data set. And they also have multiple machines for each toy class. For example, they have multiple cars, multiple conveyors, multiple trains, and that leads to variations that are inherently there between different machines of the same type, which gives you lots of different sounds for the exact same type of machine. And the data is recorded several times. So the anomalous sounds that you end up picking up tend to have diverse characteristics, which is a good thing. Ultimately, you have about 180 hours of normal machine operating sounds at over 4,048 kilohertz samples of anomalous behavior. So it gives you a fairly different behavioral pattern about what the entire data set looks like. The reason I'm talking about this is because I'm trying to highlight 2 key differences between the way the MIMI data set is done from a real-world factory data set and the toy Atmos, which is kind of done in the mock environment. While you can train models on both of them, one of the key things I want you to keep in mind is the issue of transferability. Let's say you come up with this magical model, which we'll get into next, that you can actually do anomaly detection on a given data set. We talked about transfer learning in these kinds of things. And I want you to know that the context of anomaly detection is actually quite hard to easily be able to transfer to applications of different environments. For example, if you're collecting sounds for something like how an airplane landing gear works, that data that you collect there is not easily repurposable for something like an oil rig. So keep that in mind, because sometimes anomaly detection models tend to overfit intentionally to their training data within that particular sound context. And this is just one of the pitfalls. And this is something new and different with your data engineering effort. That said, I want you to go and do the collab, and you're going to be doing some little bit of hands-on programming here. Specifically, you'll be touching upon things, around some of the thresholds that we can change, and what are the differences, in the k-means approach versus anomaly detection and so forth. And we'll be getting pretty deep into that. That said, I'm going to talk next about, how we actually build the anomaly detection model, because that's also going to be something new. It's different from the other types of networks that we've actually seen and used so far. So I'll see you there.